Now, what we're starting off today with in chapter 1 is going to seem to be a little bit all over the place. It normally is. It's going to be a little bit of everything. And once we get past chapter 1, it'll settle down where most of the other sections, so section 1, 2, 3, will more or less kind of go together. They'll flow together. And what we're looking at today is intervals and set notation. Intervals and set notation. Let me, nope, all right, that's fine. So, a set. Got it. Is a collection of objects. Braces are used to list a set's members. So you don't have to write this verbatim as long as you get an understanding of what we're talking about. So we could say, this here would be a collection, an example of a set. Yep. So, any questions on what a set is? Now we can consider the natural numbers a set because they're a group of our natural numbers, or the real numbers is a set. Now we do have a specific way that we can write sets, and that's considered set builder notation. So, there we go. Set builder notation used to define the set in terms of the properties of its members. So 1, 2, 3. Now, when we talk about set builder notation, there's a specific way that we write it. So where it says examples 1, 2, 3, and the set of whole numbers, it's not the specific example, but we're going to look at these here. So for 1, 2, 3, when we write set builder notation, we're going to write bracket X bar. So when we talk about set builder notation, this is going to be included in almost every single one. Bracket X bar. And what this says, and we look at this here, we'll look at it again in a little bit, is the set of all real numbers X such that. So this bar here is actually such that. The first part, our bracket X, is really what it's stated, is that the set of all real numbers X such that X is 1, 2, 3. And that would be set builder notation. So we're saying we have the set of all real numbers X such that X is 1, 2, 3. Now, it's probably not technically right because realistically we would just have left it as parentheses 1, 2, 3 because that's the whole set. That's all we have. Now, when we talk about whole numbers, the set of all odd whole numbers, well, unfortunately, yeah, because we wouldn't really use this. It would be more just like we did above because that's the whole set. So you can leave it. This here is not really a great way to write it. I don't like it. After I wrote it, I'm looking back at it. I don't really like this way. We would just do this here. And the reason I say that is because can we write 1, 2, 3 pretty easily? I mean, it didn't take us long to write 1, 2, 3, yes? Now, if we look at the set of all odd whole numbers are going to be 0 and greater. So some of the odd whole numbers are 1, 3, 5, 7, 9. Well, can I write all of the odd whole numbers? Well, I only listed 5, right? Well, we can keep going. Yes, 11, 13, 15, 17, 19, 21, 23. Is there any way I can list all those out? Well, no. We'd be here all day and longer than that. But that's why set builder notation is nice, because I can start off with the set of all real numbers x such that x is an odd whole number. Now, really, we would write that on one line. I wrote it on 2 because I ran out of room. But that's it. There's other ways we can write it, and we'll look at those in a minute. But this is why set builder notation is nice, is because I can define this set, this group of numbers, in a nice, easy way without having to list every single one of them. Questions on this so far? All right, now we have something known as subsets. Yep, I'll have to, let's get the biggest one. Yep. There we go. Is a set that is part of a larger set. Is when all the members of set A are also in set B. I mean, there's different ways we can say it. If you know a better way to say it in your own words, use your own words. So the main part of a subset is this right here. A subset is a set that is part of a larger set. So in this example here that we have is when all the members of set A are also members of set B. A is a subset of B. Another way we can think about that is that my classroom is a subset of the high school. Because for this high school building, everything in my classroom is contained in the high school, yes? So it is a subset of the high school. Now, everything in the subset has to be contained in the original set. I cannot say the high school is a subset of my classroom, because there are other parts of the high school that are not in my room, yes? Because Ms. Haggard's room is not contained in here, but it is a part of the high school, so I can't say the high school is a subset of this here. Now, if we look at these here, set A contains the numbers 1, 3, 15, 20, and 27, yes? Are those contained in set B? There's 1, 3, 15, 20, and 27, yes? So A is a subset of set B, because everything in A is contained in set B, yes? Is set B a subset of set A? Is there stuff in set B that is not in A? Yes. So we can't say that B is a subset of A, but A is a subset of B. Yes. Not always, but yes. Let me get this out. Because really what we're saying is 2, 11, and 100. If I took those 3 out, is A still a subset of B? Yes. Because everything in A is contained in B, yes? Now, is B a subset of A? Yeah. Because the only definition for subset is a set that is part of a larger set. It contains everything in the other set. They could be the exact same, but they are still subsets. Because the only real criteria is that anything in the subset, everything in the subset has to be in the original set. It can't contain more. So we'll go on and look at this next part, looking and naming subsets. Because subsets, there is lots of mathematics that deal with subsets and how we can define them and work with them. Now, here we're going to write all of the non-empty subsets. So a non-empty, well, an empty subset is just a subset containing nothing. And for those of you who are curious, the way that we would write an empty set would be this here. A 0 with a line through it is the empty set. But that's not that important. So when we look at this here, A, we have a set containing 4 and 5, yes? So if I wanted to write a subset of it, well, a set containing the number 4 is a subset, yes? Because everything in that set is contained in the original set 4, 5, yes? What's another one we could have? Just 5, yeah. Now there's one more. We could have the set containing what? 4 and 5. Because interestingly enough, the set itself is a subset of itself. Yeah, we can do 5, 4, or 4, 5. Here, order doesn't matter. Now, there are some cases where order would matter. Then we would specify that those are different unities. But here, 4 and 5 really doesn't make a difference. Because, well, if we were classifying, because this here is just a way to write a set, or just a group of objects. We could do this with, say, the lottery, for how the numbers roll out. In the lottery, it really doesn't matter which number comes first. As long as you get those numbers, you're good. Now, if we were doing this and writing it with, say, bingo, well, the order in which the balls come out of the chute do matter, yes? Because depending on who's going to get bingo, the order in which they occur does matter. So having A1 and then, say N40, I don't know if N40 is an actual one, those in which they occur could make a difference, because N40 could cause one person to get bingo, where B1 would cause someone else. So which order they came out matters, which would make them different. But here they don't. So 4, 5, or 5, 4 would be the same. We're going to treat it as the same. Does that kind of make sense? Did that blow your mind, Austin? Okay. Yeah. So if 4, 5, and 5, 4 were different, then we would list them. So let's see here, because I did list that here. So for the first one, we should have 3. All right, let's try the next one. So what would our subsets for this here be? C. Then we would have, and then you don't have to write these up top. These are just kind of like, did we get them all? Yes. And it'll make sense when we do one here in a minute, because we end up getting a lot very quickly. So the next one we'll look at is the numbers 2, 4, 6. Right, so we could start off with 2, then we could have 4, and then we could have 6. So I'm going to get those out of the way because those are kind of nice. We have the number 2, we have the number 4, and we have the number 6. Then we could have 2, 4, 4. Let's start with, because we could also have 2, 2, 6. Yeah, no, but then we could also have, Austin, as you were saying, 4, 6, yes? That works. If we listed before it or after it, it doesn't matter, because as long as we have it listed. So we've done 2, 4, 2, 6, 4, 6. What else could we have? So 6, 4, and 6, 2. We do. So if order mattered, yes, we would include those. But since order doesn't matter, they are the same. But the last one, 2, 4, 6. We can have the whole thing. So we would need to have 6 total. 1, 2, 3, 4, 5, 6, 7. Yep, 7. Nope, 6. What am I? 1, 2, 3. Yeah, there should be I. Because we have 1, 2, 3, 4, 5, 6, 7. Yep, those are all of them. Do we need to see another example of one of these? So this here, we would have E, we would have F, we would have G, H. We would have EF, EG, EH. Then we would have FG, FH, and GH would round out all the pairs of 2. Now we can do pairs of 3, which would be E, F, G. Yes? Then we can do E, F, H, E, G, H. Because that's one that, even if I'm not paying attention, I will miss as well. Because we still can go with E, we can just move the 2 over. Now, exactly our next one would be F, G, H. And that actually rounds off all the pairs of 3, because we can't do any other combination. Exactly. Fifteen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We got them all. Which is kind of surprising how fast that increased, because at 2, we only had 3 different pairs. 3, we have 7, and then we move up to 4, and we've got 15. So having 5 items would make it even more. Now, luckily, we are not including the empty set, because if we were, we could say the empty set is a subset of this. Yes? A set that contains nothing. Well, we could also say that we have the set containing the empty set. Because the empty set contains nothing, so the set containing this empty set would also be a subset. Are you all starting to see where this is about to go? Yeah, so we could say the set containing the empty set is also a subset of this set. So, but for none of the homework and anything that we'll do, we don't focus on the empty set. Even if the directions don't specifically state that, most of the time, actually I say most, probably all of the Algebra 2 classes don't focus on the empty set. You start talking about the empty set at more of a higher level abstract algebra kind of stuff. So what do we think about subsets? Kind of interesting. They're interesting how they work. If we want to take it a little bit further, because it is the first day, we know what this is, yes? It's a number line. Or it's what we call the real number system, yes? And a subset is any set containing everything of the other set, yes? So if I make a line going straight up and down, we now have a Cartesian plane, yes? Dealing in x, y. And this here would be this, what we write as R2, the Cartesian plane, the real number system 2. Well, this here is a subset of the number line, because everything on the number line is contained in this coordinate plane. Because that x-axis is contained in the xy, yes? Because this whole line is contained in this plane, yes? Well, XYZ, the three-dimensional plane, yes? Is a subset of R2, the XY. So we can say R3, because we reference this, XYZ is R3, which is a subset of R2, which is a subset of R1, yes? Well, according to this, we could also say that R4, whatever the fourth dimension is, would be a subset of the three-dimensional plane, which is a subset of 2, which is a subset of 1. Do we actually know how to physically represent the four-dimensional plane? No. But we could say any dimensional plane is going to be a subset of the previous one. This is actually abstract algebra, first day. We won't cover this. This won't come up on a test, but it's just kind of something interesting to think about. Let me rephrase it. It's something I find interesting to think about. So, any question on anything we've done so far? Number types. Natural numbers. Yep, so this here I spread across many different pages. And I think the note sheets might be a little bit out of order, it looks like. Okay, oh yeah, I'll have to fix the sheet, so we'll go back to that later if we do hit it at all. Now, the first set of type of numbers that we have are the natural numbers. And the natural numbers are naturally the numbers you count on your hands and your feet. So 1, 2, 3, 4, 5, 6, 7, 8. There are no decimals, no fractions, and they start with 1. Now, the natural numbers are represented by an N with 2 lines. This is the symbol for natural numbers. They're sometimes in bold, but this is the symbol for the natural numbers. Now, if you want to flip all the way to the last one where it's got everything written out, you can do that as well. Because it should be a few slides over. Yep. So if you want to write on there, you can, because we'll keep switching. I'll keep continuing switching slides. So if you want to keep rewriting it, that's fine. So where it says real numbers at the top and it's got everything, you can go there. Now, the next set that we have are the whole numbers. And the only difference between natural number and whole numbers is they add 0. That is the only difference between natural number and whole numbers is 0. The whole numbers actually doesn't have a symbol.
Can negative numbers be a whole number?
If we talk about negatives, we're actually not talking about whole numbers. No, you're good, because that's actually the next step in the process of dealing with these numbers, is integers. So natural numbers was an N with 2 lines. What do we think integers would be? It is a Z with 2 lines, which makes absolutely no sense, because we would think I with 2 lines, but it's going to be Z, because integers now adds negatives, or negative numbers. So natural is 1 and greater, whole numbers is 0, 1 and greater. Integers is our negatives and positives. So we have natural numbers, whole numbers, integers. So natural numbers was our N with 2 lines. Whole number didn't have one. Integer was a Z with 2 lines. What do we think rational numbers is? It's not going to be R. It is a Q with a line. Well, real numbers is our R. Real numbers takes R.
Okay.
Yep. So real numbers had already taken claim to that, so rational numbers gets a Q. And rational numbers are going to be any number we can rewrite as a fraction. Because when we talk about fractions, we're talking about a what? A ratio. Ratio is a fraction, a representation of 2 numbers. So rational is any number that can be rewritten as a fraction, which means, well, all of our integers are rational numbers. All of our whole numbers are rational numbers, and all of our natural numbers are rational numbers. That's why I wrote it this way, or had it set up this way, because one is contained in the other. Any questions on this so far? After irrational numbers, we get irrational numbers. And if I remember right, this is our I with 2 lines because irrational numbers. Do not quote me on this, but I have a feeling irrational numbers has been around a lot longer than some of the other numbers like integers because they came around a little bit later. And it's not that we didn't know about negative numbers. We always, or more likely, a lot of the previous cultures thought about them as the opposite number. So instead of having 4 this direction, we have the opposite of 4. Irrational, yes. The main key concept with irrational numbers, there are a number that cannot be written as a fraction, and most all of them are non-repeating, non-terminating decimals. So another one that we could have is the square root of 2 is an irrational number. Or any radical that does not reduce is going to be considered an irrational number. Because you guys should know at least one of these 3. Yes. Hopefully. Pi. Pi is the one that y'all should know. The next one is phi. It is considered to be the golden ratio. Or if you've ever seen kind of the spiral helix shape that increases as it goes out, it is one of the big numbers that we have, or kind of that we see a lot, especially in Greek architecture and sculptures, where they talk about the scaling from bigger to smaller. It's used in a lot of places. And then we will cover E later in the semester, probably in the spring semester. And it's dealing with logarithmic functions. But irrational are non-repeating, non-terminating decimals, and they're off in their own little world. Because here, any of these can be written as a fraction. Natural numbers, whole numbers, integers, or rational numbers, all of these can be written as a fraction. But irrational cannot. And most of the time we approximate these here. And the last one is our real numbers. All of these here are considered to be real numbers. And the real numbers symbol is our R with 2 lines. So that's why rational numbers didn't get the R with 2 lines, because they saved it for the real numbers. Now this does beg the question, if all of these are real numbers, what does that mean? That there's going to be some that are what? Yes. There are numbers that are not real. Now, we don't technically call them not real numbers. We call them imaginary numbers or complex numbers. And we will get into complex numbers and imaginary numbers. And the main place that we see this in kind of a more real-world application is in technology, is when real numbers do show up. Because for most everything that we have, there is a mathematical way to represent it, to represent the object or system that we have in real life. Because for any falling body, like with skydiving or anything that's coming back down to the earth, we have an equation that can represent the path of that object or what it's going to do, and to a very scientific point of view, or a very specific way that we can represent it. If we think about technology, there are ways to represent the circuits and how electricity flows through it. And if something's turned off, is there current currently flowing through it? No, but we still need a way to represent the potential energy, the potential that electricity has to flow through that circuit. And those moments are considered or defined by the imaginary numbers, or these complex numbers, the potential for something to happen, to make up for that gap of it not actually occurring. And that's one place where imaginary numbers do come in. Any questions on these here? All right. Some of this here should be kind of a recap from Algebra 1. Now we do have 2 types of intervals. One of them is bounded and one of them is unbounded. Bounded means we have 2 endpoints. Unbounded means we have 1. Yep, it's a ray. So unbounded would be considered a ray. Bounded intervals. Luckily, you don't have to write all of this here. Let A and B be two real numbers such that A is less than B. Then A and B are endpoints of four different bounded intervals on the real number line. And all that's saying that there's four different ways we can set up this bounded interval. Now the first is A is less than or equal to X is less than or equal to B. In interval notation, we use brackets. Yep. Now graphically, if we're graphing it on a number line, it would look like this here. Now the other case that we can have is A is less than X is less than B. And if we have this case, we have two parentheses. Because it's not equal to at either point. So instead of having those spots filled in, they're going to be open because it's not equal to those points. It can come all the way up to it and approach it, but it will never get to that spot. Questions on this so far? Well, the only other cases that we can have is one more time, where one of the two ends is equal to. So we can say A is less than or equal to X is less than B, or A is less than X is less than or equal to B. So I wanted to list all four possibilities that we could have with this here. Because on the one above it, it is equal to the one on the left, and the bottom one is equal to the one on the right. So it kind of switches the endpoint. Yes. You don't have to do a square. I just did squares because it's easier to do that on this here. They didn't have one where it was a filled in circle, so I just went with the square. And when we're doing these, because there will be a few of these on the homework, you don't have to put a 0 at the center to define where 0 is, because at this point, hopefully we know where 0 should be located on the number line. For any of these here, I just want the two endpoints. And the other thing is just to make sure that it is positioned where it should be. Negatives on the left, positives on the right. Smaller number on the left, bigger number on the right. I will count off if you flip it, but as long as it's the way that it should be on a number line, I will take it. Are we good with these here? Now the other set that we have are unbounded intervals. So with unbounded intervals, we're going to let A be a number. Doesn't matter what number, it's just going to be a number. On the number line shown below is called unbounded. Now there's actually 5 cases, unlike with bounded. We could have that X is greater than or equal to A, whatever the value of A is. Since it's greater, A would go on the left with a bracket, and then we would have infinity on the right. Yes? It would have to be infinity for this here, because when we talk in interval notation, we're wanting to know where is it starting, where is it ending, or what is it approaching, because here it wouldn't actually end at infinity, it would approach it. And we'll go and I have an example of exactly why we say approach and not ends. Now the other case we can have is that X is greater than A. And since it's just greater than it, we have a parenthesis at A and a parenthesis at infinity. Because if it's just greater than A, it's not including A, but everything that is bigger than it. The next one we would have is that X is less than or equal to A. Since we're talking about all the numbers smaller than A would be included because it is equal to, and all the numbers to the left. And then we could also have that x is less than a. So it would not include the point A, but have everything to the left of it. And I would accept these kind of setup as the answers for graphing of the interval notation or graphing of the inequality, as long as you didn't put A, but actually put whatever number that was signified for it. So if it was saying that x is less than 6, we would have this here, but instead of having A, we would have the number 6, and that's all I would want. Now the only other case is all real numbers. From negative infinity to infinity, it would be everything. Because we don't necessarily have an inequality version of that. We would have to use a compound inequality to be able to actually write this statement. But if we're going from negative infinity to infinity, it would be the entire number line. Any questions on any of this here? Now, we do have a few more things. I don't think we have too much more after this. Well, I think your note sheets, we have to jump back to get back to it because we skipped what was next. This one here. Yep. Yeah, I'll have to fix the note sheets. I forgot to fix them before. Let's see here. Okay. All right, that's fine. We can go through these here and look at them. So, in most of these here, I might have just left them off because y'all are used to interval notation. Yes? Remember doing in Algebra 1 a little bit? Because we talk about interval notation, we're talking about using the parentheses and brackets and putting the endpoints or points it approaches. So when we look at A, it's going from -2. It's saying -2 is less than or equal to x is less than or equal to 3. So this is inequality notation. So for interval notation, well, since it is less than or equal to, we would have a bracket, -2, comma, the other endpoint is 3. We would use a bracket because it's included. So that would be the interval notation. Questions on the first one here? Now, if we look at the second one, this is considered unbounded, unlike the first one. So we're saying what? X is greater than -1. So the smallest number we would have is -1, because x is bigger than it. We have all the numbers bigger than -1. Now, since it's not bounded, the biggest number that we could possibly approach is infinity. Now, -1, is it included? No. So we would have a parenthesis, and infinity always has a parenthesis. Questions on any of this here? No? But that's it. Let's look at the next one. So this is now in a graphical form. Now this first one here is bounded because we have two specific endpoints, yes? So if I want to write this in interval notation, we're going to have two numbers. Specifically, one is going to be -3, and the other is going to be 4. The smaller number always goes on the left, the bigger number goes on the right. Now, if we look at -3, is it included or not? Yes, because it's filled in, so this would be a bracket, because we use brackets when it's included, we use parentheses when it's not. Now, is 4 included? No. So it would be a parentheses, and that's it. Now, if we wanted to write this in interval notation with our greater than or less than, we would say that negative 3 is less than or equal to x is less than 4. Because when x is, or when we're shading in the middle, x is always going to be in the middle. When x is in the middle, we shade in the middle. We'll look at this one here. Now this here is unbounded because we have a point and it continues on in the other direction. So here, the smallest number we can actually have is negative infinity because it goes infinitely in the negative direction. Now the biggest number we have is 3, and it would include a bracket. Any questions on any of this here? We're going to stop here for today.